The rainforest hides its most serious mistakes in places that look safe. A boot left overnight at the edge of camp. A woodpile stacked to dry. A fallen palm sheath peeled back by humidity and rot. These are not dramatic locations, and that is precisely why they matter. Tarantulas do not patrol open ground or announce themselves with movement. They select shelter the same way they select defense, by minimizing effort and maximizing consequence. When you disturb one, it is never because it sought you out. It is because you entered a space it already owned. The encounter begins with proximity, not threat. You lift a boot, shift a log, peel back bark, or lean closer to inspect what you think is just another dark cavity in the forest floor. Your headlamp or flashlight cuts into the space, and there it is, a mass of hair and legs, motionless for a fraction of a second too long. That pause is deceptive. Tarantulas are not slow thinkers. They are slow movers by design, relying on sensory input and posture rather than speed. When threatened, they do not chase. They hold ground. People misread this instantly. A spider that does not flee looks manageable. Curiosity replaces caution. Someone nudges it with a stick, tries to coax it out for a better look, or reaches in to move it aside. This is where the behavior fails, not because of fear, but because of confidence. And almost without exception, the next move is the same. A hand comes up to the face. Sweat wiped away. Nose scratched. Eye rubbed. The rainforest does not need complex traps when humans repeat simple ones perfectly. Tarantulas possess one of the most misunderstood defensive systems in the animal world. Their venom is real, but rarely the primary threat to humans. Their true weapon is subtler and far more effective in close quarters: urticating hairs. These are specialized barbed setae covering the abdomen of many New World tarantula species, evolved not to kill but to contaminate. When threatened, the spider scrapes its hind legs across its abdomen, releasing a cloud of microscopic hairs into the air. This is not aggression. It is area denial. The hairs themselves are marvels of unpleasant design. Under magnification, each is a tiny spear with backward-facing barbs, engineered to lodge into skin, eyes, and mucous membranes. They are light enough to remain airborne briefly, invisible in low light, easily inhaled or deposited on exposed skin. The tarantula does not need to aim precisely. It only needs the environment to carry the payload. At first, you may not feel anything. The release is silent. No sting, no immediate pain. The problem announces itself seconds later, when the hairs settle and your body reacts. The skin prickles. The eyes itch. The nose tingles sharply, as if dust has entered too deeply. Reflex takes over. You blink hard. You rub. You wipe. Every movement embeds the hairs further, snapping barbs and driving them into tissue designed to sense intrusion quickly and loudly. This is the breath hijack moment, and it has nothing to do with venom in the lungs. The sensation is misread by the nervous system as airway compromise. Irritation around the nose and mouth triggers protective responses: coughing, shallow inhalation, rapid breathing meant to clear contaminants. The rhythm of respiration breaks. You inhale too fast, too shallow, then compensate with deeper breaths that feel wrong. The air itself seems suspect, as though it has changed quality, even though nothing external has shifted. This is panic layered onto irritation, and the body does not separate the two cleanly. Your eyes water aggressively, blurring vision and narrowing attention. Blinking becomes frantic rather than effective. Each blink presses hairs deeper into the conjunctiva. The urge to wipe intensifies, driven by the same reflexes that evolved to remove grit and debris from sensitive tissue. But these hairs are not debris. They are anchors. Every wipe spreads them across new surfaces, cheeks, lips, eyelids, multiplying the affected area. The more you try to fix the problem, the larger it becomes. From the tarantula's perspective, the exchange is already over. It has not moved from its position. It has not advanced or pursued. Its defense has done exactly what it evolved to do, create enough discomfort and confusion to make a much larger animal disengage. In the wild, this deters mammals and birds effectively. Predators learn quickly that certain shapes and textures carry consequences that are not worth repeating. Humans, again, struggle because the consequence is delayed and indirect. There is a deeper physiological layer to this response that makes it especially destabilizing. Breathing and balance are tightly linked systems. When breathing becomes rapid and shallow, carbon dioxide levels shift, affecting blood flow to the brain. Dizziness follows. At the same time, vision is compromised by tearing and blinking. In uneven rainforest terrain, roots, rocks, slick leaf litter, this combination is dangerous. People fixate on their breathing, lose awareness of footing, and stumble. The failure cascades from air to balance without any external force applied. This is not incidental. Tarantulas evolved in environments where escape routes are limited and predation pressure is constant. A defense that disrupts multiple systems simultaneously, vision, respiration, coordination, buys critical seconds and meters. It does not need to incapacitate permanently. It needs only to break focus. In ecological terms, this is efficient. It minimizes energy expenditure and reduces risk of injury to the spider itself. The rainforest amplifies the effect. Humidity keeps hairs from drying out or falling away. Sweat acts as an adhesive, trapping them against skin. Darkness reduces visual feedback, making it harder to assess what is happening and easier for the mind to assume the worst. Each of these factors compounds the response, turning a localized irritation into a full-body stress event. It is important to understand what this is not. The tarantula is not stealing your air. It is not attacking your lungs. There is no toxin shutting down respiration. The feeling of suffocation is emergent, arising from the interaction between sensory irritation and panic-driven breathing patterns. This distinction matters because it reveals the true danger. The risk is not biological failure. It is behavioral escalation in an environment that punishes loss of control. Scratching, rubbing, and frantic movement are all understandable reactions. They are also the exact responses the defense is designed to provoke. Tarantulas rely on the predictability of mammalian reflexes. They do not need intelligence or intent beyond that. Evolution has already done the modeling. Over millions of years, bodies that reacted strongly to irritation survived encounters with spiders long enough to avoid them in the future. The spider benefits from this learning curve without needing to harm permanently. Humans enter this equation without the benefit of inherited caution. We rely on curiosity and confidence instead, traits that work well in many environments and fail badly in dense, reactive ecosystems. The lesson here is not that tarantulas are dangerous predators. It is that they are effective defenders, and defense does not look like attack. As the minutes pass, the irritation slowly stabilizes if you stop interfering. The urge to wipe diminishes. Breathing begins to normalize once attention shifts away from it. But the memory of the sensation lingers, imprinting the lesson more effectively than pain alone ever could. The spider remains where it was found, unchanged, indifferent to your distress. Its role in the encounter was brief and precise. This chapter exposes a recurring pattern in rainforest hazards. The animals most capable of disrupting you are often those that do not pursue. They rely on proximity, reflex, and habit. They wait for you to complete the final step yourself. Tarantulas exemplify this strategy perfectly. They do not need speed, strength, or venom to dominate an interaction. They need only to be touched and then forgotten for a second too long. The forest does not reward curiosity without restraint. It punishes assumption. When the hairs hit your face, the danger is no longer the spider. It is the cascade of reactions inside your own body, the breathing that goes shallow, the balance that slips, the panic that convinces you something is fundamentally wrong when it is not. The tarantula does not steal your air. It simply hands the problem to your nervous system and steps out of the equation. It is not the spider that steals air, it is your panic breathing when the hairs hit your face. The rainforest's most decisive encounters happen below eye level, in the places people trust by habit. Under a strip of bark loosened by rot. Beneath a rock shifted aside for balance. Inside a boot left upright overnight. Folded into bedding, gear, or the hollow underside of a fallen palm sheath. These spaces feel inert, claimed by objects rather than animals. That assumption is what gives the centipede its advantage. Scolopendra does not stalk open ground or announce its presence. It occupies margins, compressed, dark, humid refuges where pressure and contact arrive suddenly and without warning. When the bite happens, there is no escalation phase. No warning posture, no bluff. The centipede reacts at the exact moment its body is compressed or pinned, and its response is mechanical and violent. The first pair of legs, modified into venom-injecting forcipules, drive forward like hooked blades, penetrating skin with surprising depth. This is not a single puncture. As the animal thrashes, it can deliver multiple bites in rapid succession, each driven by powerful muscles evolved to subdue struggling prey. The sensation is immediate and profound, a combination of piercing trauma and chemical invasion that the body cannot separate into neat categories. The pain is not localized. It radiates aggressively, overwhelming sensory input from the affected limb and flooding the nervous system with alarm signals. This is where the mechanism differs from insects or spiders. A centipede bite is both venomous and mechanical. Tissue damage occurs alongside envenomation, and the nervous system responds as if facing compound injury. Sweat breaks out instantly. Heart rate spikes. Muscles tense involuntarily. Shaking begins, not from fear, but from the sympathetic nervous system surging into full activation. The venom of large Scolopendra species contains a complex mix of neurotoxic and cytolytic compounds designed to immobilize prey quickly. In humans, these toxins rarely cause systemic failure, but they are extremely effective at inducing pain, inflammation, and localized paralysis. Sodium and calcium channels in nerve cells are disrupted, amplifying pain signals while interfering with normal motor control. The limb becomes unreliable within seconds. Fingers stiffen, ankles weaken. Weight-bearing becomes uncertain, just as the body demands movement. Breathing, is the next system to destabilize. The pain spike triggers a stress breath pattern almost instantly. Short, rapid inhalations, shallow chest breathing, occasional involuntary gasps as the body attempts to flood itself with oxygen for a threat it cannot locate or escape. This is not a conscious response. The respiratory rhythm is hijacked by the same alarm circuitry that accelerates heart rate and muscle tone. The sensation is tightness in the chest, not because the airway is blocked, but because breathing has lost its efficiency and depth. In this moment, the brain interprets the situation as catastrophic. Pain signals arrive faster than they can be processed. The body attempts to move, but coordination falters. Breathing becomes erratic, which further fuels panic, creating a feedback loop that locks attention inward. You are no longer navigating the environment. You are managing a physiological emergency, and the rainforest does not pause to accommodate that shift. Scolopendra evolved for exactly this type of interaction. As nocturnal predators, they hunt insects, arachnids, small vertebrates, and anything else they can overpower in confined spaces. Their long, segmented bodies allow them to wedge into crevices and apply force from multiple angles simultaneously. The bite is not meant to kill instantly. It is meant to disable, to stop movement long enough for consumption or escape. Against a human, the same principle applies. Immobilize the limb, disrupt coordination, create confusion. The escalation often comes seconds later when swelling begins. Venom-induced inflammation can cause rapid edema around the bite site, especially on hands, feet, or ankles, exactly the places relied upon for balance and grip. Shoes become tight. Fingers lose dexterity. The limb feels heavy, foreign, slow to respond. In uneven rainforest terrain, this loss of function is dangerous. A foot that cannot flex properly catches on roots. A hand that cannot grip fails to arrest a stumble. This is where breathing is stolen a second time, not by venom, but by impact. A fall knocks the wind out of you, compressing the diaphragm and forcing air from the lungs. For a moment, breathing stops entirely. When it returns, it does so in panicked gasps layered on top of an already stressed respiratory system. The body reads this as confirmation of threat. The spiral tightens. The centipede does not pursue after the bite. It does not need to. Its role in the encounter is complete. The venom continues working long after the animal has vanished back into cover. The forest now becomes the primary hazard, exploiting the vulnerabilities the bite has created. Slippery ground, sharp branches, unstable footing, features that were manageable minutes ago now become serious risks. From an ecological standpoint, Scolopendra represents a lineage that has survived largely unchanged for hundreds of millions of years. Its strategy is ancient and brutally efficient. It does not rely on speed or camouflage alone. It relies on occupying spaces where contact is inevitable and reacting faster than the nervous systems of larger animals can compensate. The centipede does not need intelligence in the human sense. It needs only to follow pressure. The shock response triggered by a centipede bite is not psychological weakness. It is a physiological cascade designed to keep animals alive in violent encounters. The problem is that in this context, the response is mismatched. Fight or flight prepares the body for running or struggling, but the environment demands stillness and control. Breathing faster does not help. Moving recklessly increases risk. Yet the body insists on both. This mismatch is where the real danger lies. People often underestimate centipedes because they are familiar, because they are not snakes or large predators, because they are usually hidden. But the combination of venom, mechanical injury, and environmental leverage makes Scolopendra uniquely capable of turning a minor disturbance into a serious incident. The centipede's effectiveness is amplified by human behavior. Boots left open, gear left on the ground, bedding not shaken out, hands placed where eyes cannot see. These are not reckless actions, they are normal ones. The rainforest punishes normalcy when it overlaps with its own routines. Scolopendra occupies the same shelters humans create unintentionally, drawn by warmth, darkness, and protection from desiccation. This overlap is inevitable, and inevitability favors the animal that reacts faster. As minutes stretch on, the pain plateaus but does not vanish. The limb remains swollen, stiff, and unreliable. Breathing gradually slows only if you force it to, which is difficult when adrenaline remains high. Sweat loss continues, increasing dehydration. The body feels drained, as if it has fought something larger than it actually has. In a sense, it has, not the centipede, but its own alarm system. This chapter reveals a layered truth about danger in dense ecosystems. The initial injury is rarely the final problem. The bite destabilizes one system, which destabilizes another until a cascade forms. First, the limb fails. Then, breathing fails. Then, balance fails. None of these failures are catastrophic alone. Together, they are. Scolopendra does not kill by venom dose. It kills by sequence. Disable movement. Trigger panic breathing. Force poor decisions. Let the environment deliver the finishing pressure. This is not malice. It is evolutionary economy. The centipede does not need speed or size to dominate an encounter. It needs proximity and compression. It waits in places people trust, reacts with overwhelming force, and disappears while the consequences unfold. By the time you understand what happened, your body is already working against you. First, it disables your limb. Then it disables your breathing by forcing the panic spiral. The rainforest does not announce danger with movement alone. Often it waits until you stop moving. The scene opens in stillness, the kind that feels peaceful only because you have not yet learned how busy it really is. Rain has just passed, leaving the understory soaked and reflective, every surface lacquered with moisture. Leaves sag under the weight of water, bark glistens dark and slick, and the air presses close to your skin with heat and humidity. In the middle of this saturated green world sits a poison dart frog, no larger than a thumb, balanced on a broad leaf like a living jewel. Its colors are impossible to ignore: electric blues, yellows, reds, high contrast patterns that seem almost artificial against the mossy browns and chlorophyll greens of the forest floor. It looks staged, as if nature itself has composed a perfect photograph and placed the frog at the center. This is the moment people remember, the still frame, the visual trophy. Bright animal, clean background, shallow depth of field in the mind's eye. Your body reacts before your reasoning does. You lean closer, shifting weight to get a better angle, steadying yourself instinctively on the nearest trunk. Your palm presses into bark that is spongy with moisture and microbial life. Sweat beads instantly across your fingers, mixing with rainwater, plant oils, and whatever invisible chemistry coats the surface of the forest. You do not touch the frog, you do not need to. The danger in this ecosystem rarely requires direct contact, and that is the first misconception that gets corrected too late. Poison dart frogs evolved to be noticed, not avoided. Their brilliance is not decoration, but declaration. These colors are an honest signal, a biological broadcast that says the same thing to every potential predator. Do not test this. The frog does not flee because fleeing would weaken the message. Stillness reinforces confidence. This animal survives not by speed or strength, but by chemistry, and more specifically by the way that chemistry moves through the environment. Its skin secretes alkaloid compounds derived from its diet, ants, mites, and other small arthropods that themselves concentrate defensive chemicals from plants and fungi. The frog is not a factory, it is a collector and distributor, a living node in a chemical network that begins with plants and ends with predators learning the cost of curiosity. What makes this encounter dangerous to humans is not the potency of the toxins alone, but the pathway they take. The frog's skin is not wet by accident. Amphibian skin is designed for permeability. It breathes through it, absorbs water through it, and regulates ions through it. The same adaptations that allow these frogs to survive in a humid, oxygen-poor understory also make their chemical defenses mobile. When the frog sits on a leaf, compounds mix with surface moisture, microscopic films spreading across veins and cuticles. The leaf becomes part of the delivery system, just as the bark you lean against becomes a transfer surface. In the rainforest, chemistry does not stay where it started, it migrates. Your hands are now part of the scene, whether you intended them to be or not. Sweat lowers friction, increases contact area, and dissolves compounds that would otherwise remain bound to surfaces. You shift again, uncomfortable, perhaps brushing water from your face or wiping your upper lip. The movement is unconscious, automatic, a reflex born of discomfort rather than decision. This is where the trap closes. The frog has not moved. The leaf has not moved. You have completed the circuit for them. The first sensations are subtle and easy to misinterpret. A faint burning at the nostrils, a sharpness in the throat that feels like inhaling humid air too fast. Your nose runs slightly. You swallow, then swallow again, trying to clear a sensation that does not behave like dust or pollen. The mucous membranes of the face, eyes, lips, nostrils, are efficient portals. They exist to absorb, to exchange, to stay wet and responsive. Alkaloid compounds do not need to enter the bloodstream in large quantities to cause problems here. Local irritation is enough. Nerve endings fire in protest, and your body responds the way it always does when it detects threat, by changing your breathing. You inhale faster, then deeper, then through your mouth, because your nose now feels unreliable, compromised. This is the breath hijack moment, not because your lungs have failed, but because your rhythm has. Breathing is both automatic and fragile. It depends on smooth feedback between airways, nerves, and muscles that expect consistency. Irritation breaks that loop. Each breath feels incomplete, as if it ends too soon or arrives too late. You try to correct it consciously, which only makes the pattern more erratic. The rainforest does not need to block your airway to make you feel like you cannot breathe. It only needs to confuse it. This is not poisoning in the cinematic sense. There is no collapse, no dramatic convulsion. What happens instead is more dangerous because it feels manageable at first. You stay upright, you remain aware. Panic builds quietly, fed by uncertainty rather than pain. Your throat feels tight, not because it is closing, but because the muscles that coordinate swallowing and breathing are now competing for priority. Saliva thickens. Swallowing feels deliberate rather than automatic. Each breath is louder than the last, and the sound alone is enough to reinforce the sense that something is wrong. In this environment, panic is not an emotion. It is a physiological multiplier. The critical error is still not the frog. It is not even the bark or the leaf. The escalation comes from repetition. Another face wipe, a scratch at the corner of the eye, a bitten nail, a chewed cuticle, a nervous habit you have performed thousands of times without consequence. Each one reintroduces compounds to sensitive tissue, extending exposure and deepening irritation. The Amazon weapon is not toxicity alone, it is timing. It waits for your second mistake, the one you make because the first one made you uncomfortable. From an ecological perspective, this system is brutally efficient. Poison dart frogs are not aggressive because aggression would cost energy and increase risk. Their survival strategy is to outsource enforcement to chemistry and behavior. Predators that attempt to eat them often survive the first encounter, but learn permanently from it, associating bright colors with nausea, muscle spasms, or worse. Humans, lacking evolutionary context for these signals, misread them as invitations rather than warnings. We see beauty and assume safety. The rainforest exploits that assumption without intention or malice. It simply continues doing what it has always done, cycling compounds through bodies, surfaces, and reactions. There is also a deeper irony at work. Many poison dart frog toxins are being studied for medical applications, including pain management and neurological research. In controlled environments, these same compounds are precision tools. In the wild, they are blunt instruments, indifferent to dosage and direction. The difference between medicine and hazard here is not chemistry, but context. The rainforest does not calibrate itself for you. It evolved for continuity, not comfort. As your breathing stabilizes slowly, as the irritation fades or becomes familiar enough to ignore, the lesson settles in with less drama than the experience deserves. The danger was never a chase or an attack. It was a chain reaction, initiated by attention and completed by habit. The frog remains where it was, still bright, still unmoved, still advertising its presence honestly. It did not deceive you. You deceived yourself by assuming that danger must be active to be real. In the rainforest, survival often depends on resisting the urge to correct discomfort immediately. Stillness is a skill here, not a default. The ecosystem is designed to punish reflex and reward patience, to turn unconscious movements into consequences. Poison dart frogs embody this principle perfectly. They do not hunt you. They do not need to. They wait for you to deliver their defense to yourself, carried on sweat and instinct, transferred by hands that were never meant to be part of the food web, but entered it anyway. In the end, the poison does not chase you through the forest, and it does not leap from leaf to skin on its own. It moves only when you move it, when you complete the final step without thinking. In this environment, awareness is protection, and restraint is the rarest survival trait of all. In the rainforest, the poison does not chase you. Your own hands deliver it to your breath. The rainforest is built from corridors. Not paths in the human sense, but narrow channels of movement carved between leaves, branches, and hanging vines, where bodies brush surfaces constantly and lightly. At shoulder height, at face height, at the exact level where sweat gathers and vision narrows, these corridors funnel everything through contact. You step into one without noticing, pushing aside a curtain of leaves slick with humidity and night condensation. The touch is gentle, almost polite. A faint tickle grazes your forearm, or the side of your neck, too mild to register as danger. You keep moving. The forest encourages this confidence. It always has. Several minutes later, the sensation returns, not sharper, just more present. A localized itch blooms where the leaf brushed you, easy to dismiss as an insect bite or plant hair. You wipe sweat from your brow, drag your sleeve across your face, press fingers briefly to the bridge of your nose. These gestures are automatic, unconscious maintenance behaviors in heat and humidity. They feel harmless because they always have been. But the rainforest does not operate on familiarity. It operates on accumulation. Hidden along that leaf corridor was not a predator in motion, but a caterpillar in waiting. Venomous caterpillars do not chase or strike. They are stillness specialists, architects of passive contact. Their bodies are armored in fields of urticating spines, hollow, brittle structures evolved to break on impact and lodge into whatever touches them. From a distance, they resemble fuzz, moss, or leaf debris. Up close, they are precision arrays, each spine angled outward like a glass needle, designed to snap and stay behind. The caterpillar's defense begins long before you feel pain. When your skin or clothing brushes the leaf it occupies, spines detach invisibly, clinging to fabric fibers, skin oils, and moisture. You do not need to touch the caterpillar itself. The leaf becomes an extension of its body, a delivery platform. This is the ecological genius of these larvae. They outsource defense to the environment, turning plants into intermediaries and movement into exposure. At first, your nervous system treats the intrusion as noise. The itch is shallow, ambiguous, not yet meaningful. 10 minutes pass. Then the sensation deepens, transforming from itch to heat, from surface irritation to a burning that feels oddly internal, as if the skin itself is reacting rather than what lies on it. This delay is not accidental. Urticating spines embed like microneedles, anchoring into the upper layers of skin and releasing compounds slowly. Some species, such as the infamous Lonomia caterpillars, carry toxins capable of far more severe effects, but even less potent species are effective at creating sustained discomfort through mechanical and chemical persistence. Your brain reassesses. Burning signals threat. Threat demands attention. Attention demands action. You scratch. This is where the caterpillar's real trap activates. Scratching does not remove the spines. It drives them deeper, snaps more of them, and spreads them across a wider area. Fingertips collect fragments and transport them efficiently, transferring spines from arm to neck, from neck to face, from face to eyes and nostrils. The upper lip becomes a hotspot, rich in nerve endings and moisture. The nose tingles sharply. The eyes water. The forest air suddenly feels thick, hostile, as if something has changed in the environment rather than on your skin. Breathing shifts without permission. The irritation around your nose encourages mouth breathing, which is faster and less controlled. Each inhale feels slightly raw, as if the air itself carries grit. The sensation is not obstruction. Nothing is blocking your airway. But the body does not distinguish cleanly between irritation and danger. Your respiratory rhythm becomes uneven. You inhale too quickly, exhale too shallowly, then try to compensate with deeper breaths that arrive late and feel unsatisfying. This mismatch feeds anxiety, and anxiety feeds respiration in a loop that tightens rather than resolves. The breath hijack here is subtle and insidious. It is not driven by venom acting directly on the lungs, but by sensory overload at the face, the command center for breathing decisions. The nose, eyes, and upper lip are critical reference points for airflow. When they burn or sting, your brain interprets breathing as compromised, even when it is not. The result is hyperventilation layered on irritation, producing the deeply unsettling feeling that you cannot get a clean breath, no matter how hard you try. Ecologically, this strategy makes perfect sense. Caterpillars are slow, soft-bodied, and defenseless in every way that predators usually exploit. They cannot flee or fight. Instead, they weaponize contact itself. Urticating spines discourage predators after a single interaction, teaching birds, mammals, and even insects to avoid their silhouette and texture. Bright coloration in some species reinforces this lesson, while cryptic camouflage in others relies on the same mechanism without advertisement. Whether seen or unseen, the outcome is the same. A predator learns that touch equals consequence. Humans, again, fall into the gap between signal and understanding. We do not recognize the warning textures encoded in these bodies because our evolutionary history did not require it. We assume that danger announces itself clearly or immediately. Venomous caterpillars violate both assumptions. Their effects escalate over time, and their delivery depends on our own behavior. Clothing becomes a reservoir, trapping spines in fabric we later press against bare skin. Towels, backpacks, bedrolls all become secondary exposure vectors, capable of reactivating the burn hours later in entirely new locations. The rainforest amplifies this persistence. Humidity keeps skin hydrated and permeable. Heat increases blood flow to the surface, intensifying sensation. Sweat dissolves and redistributes compounds. In these conditions, the body struggles to isolate the problem. Every attempt to soothe, wiping, rubbing, scratching, extends the exposure window. The caterpillar's defense is not a spike of pain, but a prolonged disruption that exhausts attention and erodes calm. There is an evolutionary elegance to this system that is easy to miss when focusing only on discomfort. Caterpillars occupy a critical position in rainforest food webs, converting plant matter into animal biomass and serving as prey for countless species. Their defenses must be effective enough to allow survival without rendering them untouchable to all predators. Urticating spines strike that balance. They punish careless contact, but do not poison entire ecosystems. They rely on learning rather than lethality. For humans, the danger lies less in toxicity than in misinterpretation. The burning skin and disrupted breathing feel urgent, even catastrophic, but they are primarily signals. The real risk comes from panic-driven behavior in an environment that demands precision. Hyperventilation can lead to dizziness. Scratching can break skin, increasing infection risk. Loss of composure can cause falls, disorientation, or further exposure to other hazards. The caterpillar does not need to incapacitate you. It only needs to destabilize you. As minutes stretch, the burn pulses rather than fades, flaring whenever touched, quieting only when left alone. This teaches a lesson the rainforest enforces repeatedly. Stillness is corrective. Restraint interrupts the feedback loop. But restraint is difficult when the body insists something is wrong. That insistence is the caterpillar's true weapon. It turns your own sensory systems against you, transforming protective reflexes into liabilities. From a distance, the caterpillar remains what it always was, a small, slow-moving larva, engaged in the simple act of feeding. It does not pursue you. It does not react to your distress. Its evolutionary role is complete the moment the spines detach. Everything that follows is managed by your physiology and your choices. The rainforest provides the stage, the caterpillar provides the trigger, and your nervous system performs the rest. This chapter of contact-driven danger reveals something fundamental about survival in dense ecosystems. Threats do not need to be dramatic to be effective. They do not need teeth, speed, or intent. They need only to exploit habit. A single brush, a single wipe, a single scratch is enough to turn skin into a battlefield and breath into an adversary. The caterpillar does not need venom fangs or a striking posture. It does not need to chase or bite. It waits, armored in needles finer than thought, trusting that movement will do what aggression never could. Just one wipe, and your breath becomes your enemy. The rainforest teaches balance through contact. Every step is negotiated with roots, trunks, vines, and hanging stems that exist exactly where you need to place your weight. You lean without thinking, palm flat against bark still warm from the day, fingers curling around a vine slick with condensation. This is not carelessness. It is how movement works here. The forest is vertical and unstable, and your body adapts by distributing trust across many surfaces at once. That adaptation is exactly what the bullet ant exploits. The sting does not announce itself with warning. There is no build-up, no gradual escalation. 1 second your hand is supporting your weight, the next, the world collapses inward around a single point of contact. The sensation is immediate, absolute, and impossible to contextualize. It does not feel like skin damage. It feels like a system failure. Pain detonates, not spreading outward, but overwhelming inward, flooding the nervous system so fast that the brain cannot prioritize anything else. People often describe bullet ant pain using metaphors, gunshots, electricity, fire, but these comparisons miss the critical detail. This pain is not just intense, it is disruptive. The venom of the bullet ant contains toxin, a neurotoxic peptide that interferes with sodium ion channels in nerve cells, forcing them into a state of uncontrolled firing. The result is not injury in the traditional sense, but overload. Sensory neurons scream continuously, drowning out all other signals. The body loses its ability to interpret proportion. In that moment, coordination vanishes. Fingers release their grip reflexively. Muscles tighten without instruction. Your posture collapses because the nervous system is no longer distributing control evenly. Everything you are doing, standing, breathing, balancing, becomes secondary to processing the incoming pain signal. This is not weakness. It is biology behaving exactly as designed. Pain exists to demand attention, and bullet and venom demands all of it. Breathing is the first system to fail cleanly. Not because your lungs are affected, but because respiration depends on rhythm, and rhythm requires bandwidth. The instant the sting lands, your breathing fractures. A sharp inhale cuts off halfway. Another follows too quickly. Panting replaces depth. Involuntary gasps punch through attempts at control. This is the breath hijack moment in its purest form. Within seconds, your respiratory pattern is no longer automatic. It is reactive. This matters because oxygen delivery is tied to composure. Rapid, shallow breathing reduces efficiency, altering carbon dioxide balance and amplifying the sensation of panic. The pain convinces your brain that something catastrophic is happening, and the breathing pattern confirms it. Each ragged breath reinforces the idea that control has been lost. The feedback loop locks in fast. The bullet ant does not rely on chance placement. It lives and forages exactly where hands go. Tree trunks, buttress roots, vines, and low branches are highways for these ants, which can grow over 2 centimeters long and move with deliberate confidence. Colonies are spread out, not densely packed like some ant species, which means encounters are isolated but severe. One sting is enough. There is no swarm needed. This is a precision defense. Ecologically, the bullet ant occupies a fascinating niche. It is both predator and defender, hunting insects and small arthropods while maintaining territorial control over vertical space. Its sting is not designed to kill large animals. It is designed to teach them instantly and permanently. Few predators attempt a second interaction. Even mammals with thick fur learn quickly that certain trees are not worth climbing. Pain here is not lethal, it is instructional. For humans, the instruction arrives too late to prevent escalation. Heat accelerates everything. Within moments of the sting, sweat erupts across your body, driven by stress hormones and temperature regulation gone haywire. Sweat loss increases dehydration, which thickens blood slightly and raises heart rate further. Your breathing speeds up again to compensate. You feel hot, unsteady, overwhelmed. The rainforest, already demanding in calm conditions, becomes hostile when your internal systems are misfiring. Decision-making degrades fast under these conditions. People make the same errors repeatedly. They run without looking. They grab more vegetation for support, exposing themselves to more ants, thorns, or unstable footing. They fall, not because the terrain changed, but because coordination is no longer synchronized with intention. Hands shake. Vision narrows. The pain does not fade. It plateaus at an intolerable level and stays there. This is where the bullet ant strategy reveals its full efficiency. It does not need prolonged venom delivery. The toxin binds quickly and forces nerve cells into prolonged excitation. Pain can last for hours, sometimes longer, but the critical window is the first minute. That is when breathing breaks, balance falters, and the risk of secondary injury skyrockets. The ant has already succeeded before the person understands what happened. There is no inflammation explosion, no dramatic swelling that signals danger visually. The skin may look almost unchanged. This disconnect between sensation and appearance is deeply unsettling. It undermines confidence in assessment. If it hurts this badly, surely something catastrophic must be happening. The brain searches for explanations and finds none, which further fuels panic. This is how control is stolen, not by physical damage, but by uncertainty layered onto pain. Bullet ants are famous among indigenous cultures of the Amazon, not as curiosities, but as benchmarks. Some initiation rituals use controlled exposure to bullet ant stings precisely because they represent a known maximum of pain that does not usually cause permanent damage. This cultural context matters. It demonstrates that the sting is survivable, but only with preparation, restraint, and understanding. Without those, the same sting becomes a destabilizing force that can turn a routine movement into an emergency. From a physiological standpoint, the venom's effect on breathing is indirect but profound. Pain activates the sympathetic nervous system, triggering fight or flight responses that prioritize speed over efficiency. Breathing becomes shallow to allow rapid oxygen intake for muscles that think they need to act immediately. But in a forest environment, rapid action without coordination is dangerous. The body prepares for sprinting when it should be preparing for stillness. The bullet ant does not chase you after the sting. It does not need to. The interaction is complete. Its role in the event ends the moment the venom enters your system. Everything that follows, panic breathing, dehydration, poor decisions, is handled by your own physiology. This is the hallmark of an evolved defense: minimal effort, maximal consequence. As minutes pass, the pain does not diminish. It pulses, throbs, and radiates, making it difficult to rest or regain composure. Breathing gradually slows only if you force it to, which is difficult when every nerve is firing. The rainforest does not offer comfort. Humidity prevents cooling. Insects continue to land. The ground remains uneven. You are required to manage an internal crisis while navigating an external maze. This chapter is not about venom lethality. It is about control. The bullet ant's sting strips fine motor coordination first, then gross motor stability, then calm breathing. Hands become unreliable. Breath becomes erratic. Thought narrows to endurance. In this state, even experienced people are vulnerable to compounding errors. The ant does not kill with venom. It kills with disruption. By hijacking your nervous system, it steals your ability to interact safely with the environment around you. The forest does the rest. Roots trip you. Slopes destabilize you. Heat drains you. None of these are threats on their own. Together, under pain-driven chaos, they become lethal. This is the final truth of the bullet ant. Its power lies not in toxicity, but in timing. It strikes when your hand is committed, when your weight is shifting, when your balance depends on uninterrupted control. In those seconds, breathing and movement must cooperate perfectly. The sting ensures they do not. The ant does not kill you with venom. It kills you by stealing control of your breath and your hands. Night changes the rules of the forest without changing its shape. The trail you walked safely an hour ago now feels narrower, heavier, as if the darkness itself has weight. Headlamp beams carve thin tunnels through humid air, catching drifting insects and the reflective eyes of things that do not move when seen. The ground still holds the day's heat, releasing it slowly through damp soil and decaying leaves. And every step presses moisture back up through the soles of your boots. Somewhere nearby, frogs call in overlapping pulses, a soundscape so constant it fades into background, until one sound doesn't. A low, wet shuffle interrupts the rhythm ahead, and your light lands on a broad, unmoving shape planted directly in your path. The marine toad does not flinch. It sits squarely in the beam, massive for an amphibian, squat and confident, its warty skin catching highlights like dull stone. This animal has learned something important about humans. We expect movement to indicate danger. When something does not move, we assume control. The toad's posture feels almost confrontational, not because it advances, but because it refuses to yield. On trails and at camp edges, this moment plays out the same way again and again. People hesitate, then laugh, then make the same poor decision with minor variations. Pick it up, push it aside with bare hands, or nudge it with a foot and steady themselves with a palm against a nearby trunk. The mistake is not malice or curiosity. It is normalization. Marine toads have expanded far beyond their native range, especially in places like Australia, where they are now a dominant nocturnal presence around human spaces. Their abundance dulls caution. They are big, obvious, slow. They look like obstacles, not hazards. But this species did not become successful by accident. Its survival strategy is tuned precisely to moments like this, when a larger animal interacts without respect for boundaries. The skin of a marine toad is not simply a barrier. It is an interface. Along its shoulders sit enlarged parotoid glands, visible as raised pads behind the eyes, but the entire body surface participates in chemical defense. These toads secrete a milky cocktail of toxins, cardioactive steroids, alkaloids, and irritants that evolved to deter predators large enough to swallow them whole. Unlike venom, which requires injection, these compounds rely on contact. They are designed to contaminate mouths, eyes, and mucous membranes when a predator bites down or paws at the wrong place. The toad does not aim. It coats. When you touch the toad, or the damp ground it has just crossed, or the bark it brushed while moving through camp, you do not feel anything dramatic. The skin feels cool, rubbery, unpleasant, but not alarming. You wipe your hands on your pants, already damp with sweat. Maybe you forget entirely and continue walking. Maybe you reach camp and grab food, or lift a bottle, or swipe sweat from your face without thinking. This is where the mechanism activates, not as a sudden strike, but as delayed relevance. Sensitive tissue reacts faster than skin. The inside of the mouth, the throat, the thin membranes of the lips and nostrils, all are densely innervated and designed to respond quickly to chemical change. Irritation begins as a sharp taste, slightly bitter, slightly metallic, followed by warmth that feels out of place rather than painful. The body interprets this as intrusion. Salivary glands surge. Muscles in the throat tighten reflexively, initiating a swallow meant to clear whatever does not belong. This reflex collides with breathing, which momentarily pauses to avoid aspiration. For a fraction of a second, your airway feels occupied, not blocked, but uncertain. That uncertainty is enough. You gasp, not because you lack air, but because your nervous system demands confirmation. The inhale is shallow and fast, drawn through a mouth that now feels wrong, coated, unfamiliar. Each breath seems to scrape slightly, irritating tissue that was never meant to encounter these compounds. The sensation does not escalate linearly. It flickers. A breath feels fine, the next does not. This inconsistency is what triggers anxiety. The brain struggles more with unpredictable signals than with constant pain, and so attention narrows onto the act of breathing itself. Heat amplifies everything. Sweat increases absorption and spread, keeping compounds mobile on the skin. Humidity prevents evaporation, prolonging contact. In tropical nights, you cannot dry your hands easily, even if you try. Every wipe of the face becomes a reapplication, a small renewal of irritation. Contact lenses, if present, turn eyes into reservoirs, trapping residues against the cornea and extending exposure far beyond the initial mistake. Rubbing harder does not remove the problem. It redistributes it, spreading compounds across a wider surface and deeper into sensitive tissue. From the toad's perspective, nothing unusual has occurred. It has not sprayed, lunged, or chased. The idea of a targeted attack is a human projection, shaped by stories rather than biology. The toad's defense is passive but persistent. It relies on others to mishandle it, to underestimate the power of contact, to treat chemistry as something that must be injected or ingested in large quantities to matter. In reality, the effectiveness of these secretions lies in how they interact with reflexes. Swallowing, gasping, wiping sweat. These are ancient behaviors, deeply ingrained and difficult to suppress under stress. Marine toads are ectotherms, their activity governed by external temperature. Nighttime warmth allows them to roam, forage and breed efficiently, often congregating near artificial lights that attract insects. Human camps become feeding grounds, and trails become corridors. This overlap is not incidental. It is an ecological collision between a species adapted to exploit edge environments and humans who underestimate how porous those edges are. The toad thrives in disturbed landscapes precisely because it does not require concealment. Its chemical shield allows it to occupy open ground with minimal fear. There is a broader lesson embedded here about how danger operates in the natural world. The most effective defenses are often those that turn an opponent's biology against itself. Marine toads do not need to incapacitate predators outright. They only need to make the act of interaction unpleasant enough to be remembered. For humans, memory is reinforced by panic, and panic is reinforced by disrupted breathing. Once your airway feels unreliable, everything else fades in importance. Rational assessment becomes harder. Movements become faster and less precise. Each attempt to fix the problem risks deepening it. The escalation can last far longer than expected. Even as the initial irritation subsides, heightened awareness keeps breathing shallow and guarded. You avoid full inhalations, unconsciously bracing for discomfort that may no longer be there. This pattern can persist for minutes or hours, especially in heat, where exertion and dehydration add stress. The danger is no longer the toxin itself, but the cascade it initiated. Poor breathing leading to dizziness, clumsy movement, and further mistakes in an environment that punishes inattention. Ecologically, marine toads are a study in how simple strategies can dominate new environments. Their reproductive output is enormous, their diet broad, and their defenses universally applicable. They do not need specialized predators or complex behaviors to survive. They need only to persist and be mishandled. In places where native predators lack evolutionary experience with toxins, the consequences are often fatal for the predator and reinforcing for the toad population. Humans, despite intelligence and technology, are not exempt from this mismatch. We are simply less likely to die from it and more likely to dismiss it as a minor incident, until it happens again. The quiet cruelty of this trap lies in its ordinariness. There is no drama in nudging a toad off a trail, no sense of risk in wiping sweat from your brow, no warning sign in the first swallow that feels slightly off. The marine toad exploits the gap between cause and effect, between touch and consequence. By the time you feel something is wrong, the moment of prevention has passed. In the end, the toad does not need speed, venom, or aggression. Its entire strategy is built around patience and inevitability. It waits for contact, coats whatever touches it, and trusts the environment to do the rest. Heat, humidity, habit, and reflex complete the loop. The forest does not require elaborate traps when simple ones work so reliably. The marine toad's defense is not about overpowering you. It is about making your own hands untrustworthy, turning the most familiar tools you have into vectors. Once that happens, the outcome is no longer in the toad's control or even its concern. The final step always belongs to you. The toad's trap is simple. Make your hands toxic, then wait for you to touch your breathing holes. The rainforest floor is never empty. It only pretends to be. From above, the ground looks calm. Dark soil, scattered leaves, roots threading through like old veins. But at knee level, at the height where humans pause, rest, kneel, or adjust their footing, the forest is already moving. Leafcutter ant trails are not obvious until you are inside them. They do not announce themselves with noise or aggression. They reveal themselves through contact, through the sudden realization that the ground beneath you is not passive. The moment usually begins with stillness. You stop to tighten a strap, to catch your breath, to steady yourself on uneven terrain. You kneel without thinking, or shift your weight back onto a log, or step sideways to avoid a branch. There is no warning posture, no visual threat display. The ants do not rush at you as a predator would. They simply continue doing what they were already doing, flowing. Leafcutter ants are architects of motion. Their trails are living infrastructure, carved into the forest floor and reinforced by constant traffic. Thousands of workers move in organized lanes, carrying leaf fragments many times their own weight, feeding a subterranean fungal agriculture that sustains the colony. This is not chaos. It is precision at scale. And when a large animal enters that scale, the system does not adapt. It overwhelms. The first sensation is mild. A tickle. A pinch. Something sharp but small. Then another. Then several more, arriving too fast to count. Leafcutter ants do not rely on a single powerful bite. Their mandibles are designed for cutting plant tissue efficiently, and human skin is not much of a challenge. Each bite produces a tiny incision, a shallow wound that stings sharply but briefly. One would be insignificant. 50 are not. Your skin becomes a map of points, each demanding attention. Ankles, calves, knees, hands, any exposed area within reach of the trail lights up. The nervous system attempts to track each sensation individually and fails. Attention fragments. You try to brush them off, slapping at your legs, sweeping your hands across your clothing. The ants cling stubbornly, jaws locked, bodies swinging as you move them. Each removal triggers another sting nearby as more ants flood the disturbance. This is not an attack in the animal sense. There is no intent, no pursuit. The ants are responding to vibration and obstruction, following simple rules executed by thousands of individuals at once. That is what makes it effective. The colony does not need to recognize you as a threat. It only needs to continue operating at full capacity while you attempt to interrupt it. Breathing begins to change almost immediately, not because of pain alone, but because of unpredictability. Each new bite lands at a different location, breaking rhythm and concentration. You inhale sharply as one catches the back of your knee. You exhale too fast as another stings your wrist. Your breathing loses cadence, becoming reactive rather than regulated. This is chaos breathing, panting shaped by flinching rather than need. As you swipe at your legs, you inhale debris without noticing. Fine dust rises from the forest floor, mixed with spores, soil particles, fragments of dried leaf. Each breath comes in through an open mouth, fast and shallow, unfiltered by the nose. The air feels thick, scratchy. Your chest tightens slightly, not from obstruction, but from effort and alarm. The sensation that something is wrong with your breathing takes hold, even though your lungs are functioning normally. The ants amplify this response by refusing to let it settle. There is no pause between bites. The field of sensation remains active, forcing constant movement. You cannot stop and reset your breathing because the moment you do, another sting demands attention. Your body remains locked in a low-grade fight-or-flight state, burning energy inefficiently and losing coordination with every second. Leafcutter ants evolved for exactly this kind of interaction. They are not defenders in the traditional sense. Their power lies in numbers and persistence, not in venom or strength. Individually, they are fragile. Collectively, they dominate vast territories, clearing vegetation, shaping soil structure, and outcompeting other herbivores through sheer efficiency. Their mandibles cut not only leaves, but also pathways, altering microhabitats and nutrient flow throughout the forest. When a large animal disrupts a trail, the ants do not retreat. They surge. The same behavior that allows them to transport tons of vegetation annually allows them to overwhelm intrusions without coordination or leadership. Pain becomes a byproduct of scale. Enough small injuries, delivered fast enough, can destabilize even a much larger organism. The escalation rarely comes from the bites themselves. It comes from movement. As the stinging intensifies, you step backward without looking, trying to escape the source. Your attention is on your skin, not the ground. Roots catch your heel. Leaf litter slides. You lose balance and fall, landing hard on your back or side. The impact knocks the wind out of you, compressing the chest and forcing air from the lungs in a sudden, involuntary exhale. For a moment, breathing stops entirely. The diaphragm spasms, refusing to reset. When air finally rushes back in, it does so in a panicked gasp, layered on top of already erratic respiration. The body reads this as confirmation of danger. Heart rate spikes again. Muscles tense. You scramble to get up, still surrounded by ants, still breathing poorly, still flinching. This is how leafcutter ants steal breath without ever touching the airway. They create the conditions for a fall, and the fall does the rest. The swarm does not need venom. It does not need a coordinated strike. It needs only to fragment attention long enough for gravity and terrain to take over. Ecologically, this strategy has consequences far beyond human encounters. Leafcutter ants shape rainforest dynamics on a massive scale. Their fungal gardens depend on constant input, and their trails are among the most stable structures in the forest floor, persisting for decades. Animals that learn to avoid these trails survive encounters more efficiently. Those that do not are repeatedly punished until the lesson sticks. Pain here is not fatal. It is corrective. Humans struggle because our size and intelligence give a false sense of immunity. We assume that small animals cannot impose meaningful risk. Leafcutter ants exploit this assumption relentlessly. They do not need to stop you. They only need to disrupt you long enough for your own reactions to create the hazard. There is a particular cruelty in how ordinary this all feels in retrospect. No dramatic bite, no venomous sting with a clear source, just a series of small, sharp sensations that spiral into loss of control. The memory often focuses on the fall, the breath knocked out, the scramble to recover. The ants fade into background noise even though they initiated the sequence. From a physiological perspective, this chapter reveals how fragile breathing is under stress. Efficient respiration depends on rhythm, posture, and calm. Break any one of those and the system degrades. Leafcutter ants break all three simultaneously. They force constant movement, disrupt posture, and provoke anxiety through unpredictable pain. The result is a respiratory pattern that cannot stabilize until the stimulus ends. The rainforest reinforces this effect. Humidity makes the ground slick. Uneven terrain multiplies the risk of missteps. Heat accelerates fatigue and dehydration, reducing your margin for error. By the time you regain composure, the ants have already returned to their work, uninterested in the outcome. Their system absorbed the disturbance and moved on. This chapter is not about insects overpowering humans. It is about systems overpowering individuals. Leafcutter ants represent swarm logic at its most effective. No single point of failure, no need for escalation, no reliance on lethal force. They turn the environment itself into a weapon by forcing you to interact with it poorly. The lesson here is not to fear ants. It is to respect scale. In the rainforest, danger often arrives as math rather than muscle. Enough small inputs, delivered quickly enough, can dismantle control faster than any single blow. The swarm does not need power. It needs timing. It needs distraction. It needs you to breathe wrong and move wrong at the same moment. That is the real weapon of leafcutter ants, the arithmetic of overwhelm, where pain adds up faster than you can adapt. It is the swarm math. They do not need power, just enough pain to make you breathe wrong and move wrong. Water changes the rules faster than any animal ever could. At the river's edge, the rainforest loosens its grip just enough to feel forgiving. Canoes drift instead of stumble. Feet slide instead of snag. The surface looks open, navigable, almost cooperative compared to the tangled understory behind it. That illusion is what draws people too close. Narrow channels, quiet bends, sandy banks that slope gently into brown water. All of it suggests access, not danger. But rivers are not neutral space. They are owned. Giant otters are not ambush predators in the human imagination. They are playful, social, vocal, almost charismatic. They surface in groups, roll through water, slap tails, and chirp to one another with an energy that reads as curiosity rather than control. That misreading is the first mistake. Giant otters are not tolerant neighbors. They are territorial mammals defending linear real estate, and water is the most unforgiving environment in which to test boundaries. The encounter often begins without tension. A canoe glides into a narrow side channel where vegetation presses close on both banks. Or someone wades into waist-deep water near a bank that looks stable, calm, unused. Dens are easy to miss. Low openings in the earth just above the waterline, hidden by roots and overhangs. To an otter group, proximity to a den is not a curiosity. It is a violation. The response is immediate and coordinated. Heads rise from the water almost simultaneously. Bodies align. Vocalizations erupt. Sharp barks and screams that carry across water far more efficiently than through forest. These sounds are not warnings meant to scare. They are rally signals. Giant otters do not bluff alone. They confront as a unit. At this point, many people freeze or drift, assuming that stillness equals de-escalation. In water, stillness does not erase presence. Current carries you. Canoes drift. Waders sway. Distance closes without effort. The otters do not need to rush. They advance with purpose, bodies low in the water, eyes fixed, heads tracking movement with unsettling precision. The danger here is not just teeth. It is context. Even minor physical contact becomes amplified by the environment. Water adds an extra rule to every encounter. Breathing must remain perfectly timed. One mistake, one inhale at the wrong moment, and the problem escalates instantly. When contact occurs, it is fast and disorienting. An otter lunges, slams into a canoe, grabs a paddle, or strikes at a leg. The force itself may not be catastrophic, but it destabilizes posture immediately. Canoes rock violently. Feet lose traction on submerged mud. Balance disappears in a medium that offers no friction to recover it. This is the breath hijack moment. At the surface, struggle creates splashing, spray, and involuntary gasps. Water enters the equation at exactly the wrong time. Panic breathing becomes dangerous breathing. Each sharp inhale risks aspiration. Each exhale disrupts buoyancy and timing. The body's instinct to breathe faster under stress becomes a liability when air and water are interleaved. The sensation is not choking in the traditional sense. It is the terrifying uncertainty of whether the next breath will be air or water. Your lungs hesitate. The brain cannot synchronize movement and respiration. You inhale too early, swallowing water. You cough reflexively, expelling air when you need it most. The rhythm collapses. Giant otters are perfectly adapted to exploit this environment. Their bodies are streamlined, muscular, and built for acceleration and control in water. Dense fur insulates them thermally, allowing prolonged exertion. Webbed feet and powerful tails generate precise thrust. Their lungs and blood chemistry are tuned for diving, allowing them to hold breath calmly while others panic. They do not need to submerge you intentionally. They only need to keep pressure on long enough for you to fail at breathing. As panic escalates, orientation disappears. Surface reflections confuse vision. Turbid water hides depth. Sound becomes distorted, replaced by splashing and internal noise, heart pounding, breath rasping, coughing. The sense of up and down weakens. People flail, arms breaking the surface in inefficient arcs, legs kicking without traction. Each movement increases water intake risk. Seconds matter here. Not because of venom, not because of bleeding, but because oxygen deprivation compounds quickly when breathing is compromised by environment rather than injury. Even strong swimmers are vulnerable when panic hijacks respiration. Muscle memory dissolves. Techniques vanish. Everything becomes effort without effect. From the otter's perspective, this is controlled chaos. Giant otters are apex predators of fish and aquatic prey, accustomed to wrestling slippery bodies in 3 dimensions. Their bites are strong, their coordination exceptional, but their true advantage is composure. They are not panicking. They are operating in their native medium. Territorial defense in giant otters is intense because it must be. River systems are linear resources. A den site offers safety, breeding space, and access to fish stocks. Losing control of a stretch of river has immediate survival costs. Groups that hesitate lose ground. Groups that act decisively maintain it. Evolution favors assertiveness. Humans misinterpret this because the attack does not look like predation. There is no silent stalk, no ambush from below. Instead, there is noise, visibility, apparent warning. People assume that if they can see the animal, they can manage the situation. Water removes that advantage. Visibility does not equal control when breathing is compromised. Escalation accelerates through instinctive mistakes. People try to push otters away, bringing faces closer to the surface. They shout, expelling precious air. They thrash, inhaling spray. Canoes flip. Bodies go horizontal when vertical posture is needed to keep the airway clear. Each error feeds the next. Even without direct bites, the environment does the work. Aspiration triggers coughing fits that make coordinated swimming impossible. Swallowed water induces nausea and dizziness. The body enters survival mode, prioritizing immediate air over strategy. At this point, the encounter is no longer about animals. It is about physics and physiology. Ecologically, giant otters are indicators of healthy river systems. Their presence reflects abundant fish, intact banks, and low pollution. They are cooperative hunters, coordinating movements and vocal signals to corral prey. The same coordination makes them formidable defenders. What appears playful at a distance becomes overwhelming up close. The irony is that many dangerous encounters occur because people underestimate how quickly water turns neutral actions into fatal ones. Wading seems controlled. Canoes seem stable. But stability in water depends on constant micro-adjustments of breath and posture. Disrupt either, and collapse follows rapidly. As the situation resolves, either through retreat, separation, or sheer luck, the body remains shaken long after physical contact ends. Breathing takes minutes to normalize. Coughing persists. Muscles tremble. The memory is dominated not by pain, but by air hunger, the primal terror of not knowing if the next breath will work. This chapter exposes a harsh truth about wildlife encounters near water. Teeth matter. Strength matters. But neither decides the outcome as quickly as breathing does. In aquatic environments, every conflict is filtered through respiration. Lose control of breath, and everything else becomes secondary. Giant otters do not need to maul to be lethal. They do not need prolonged engagement. They need proximity in water and a moment of panic. The river enforces the rest. Near water, the fight isn't teeth. The fight is your next breath. The rainforest understory is not built for speed. It is built for resistance. Every meter is layered with stems, vines, saplings, buttress roots, and fallen debris that turn straight lines into illusions. Visibility collapses beyond a few body lengths, sound bends unpredictably, and movement is always filtered through obstacles. This is where the peccary thrives and where human instincts fail most reliably. The first sign is rarely visual. It is a sound that does not resolve cleanly, rustling that is too heavy for birds, too widespread for a single animal. A low chorus of movement ripples through the vegetation, punctuated by grunts and the dry crack of snapping stems. Shapes flicker between leaves, not one or two, but many, moving with a density that feels wrong. Your brain reaches for familiar categories: deer, pigs, something fleeing. But the pattern does not match escape. It feels cohesive, directed. Peccaries do not scatter when threatened. They compress. This is the critical misunderstanding. Peccaries are not solitary animals reacting independently. They are herd organisms, bound by proximity, vocalization, and scent. When danger appears, they do not rely on speed or concealment. They rely on pressure. Bodies pack together, heads drop, tusks align, and movement becomes unified. What looks like chaos from the outside is in reality a wall forming. The classic human mistake happens immediately. You run straight and fast, committing to a line that exists only in your head. You do not scan for lateral exits. You do not assess footing. You simply accelerate, believing that speed equals safety. In open terrain, that instinct might work. In dense understory, it burns oxygen faster than it buys distance. Peccaries evolved for this environment. Their bodies are compact and muscular, built to push through resistance rather than glide over it. Short legs, low center of gravity, and thick hides allow them to plow through brush without hesitation. Their hooves strike roots and stones without the delicate recalibration humans require. They do not need clear lanes. They create them. When a defensive charge begins, it is not a sprint. It is a surge. The herd advances as a mass, not necessarily to pursue, but to clear space. Pressure is the weapon. The intent is not predation. It is displacement. Anything in the way is something to be moved, trampled, or knocked aside. The breath hijack moment arrives faster than expected. Sometimes it is physical, a shoulder or chest collision that knocks the wind out of you instantly. Air explodes from the lungs in a forced exhale, leaving nothing behind. For several seconds, breathing is impossible. The diaphragm locks, stunned by impact, and panic spikes as the body waits for the reflex to reset. But even without contact, the hijack is inevitable. Sprinting in humid rainforest heat creates oxygen debt almost immediately. The air is heavy with moisture, reducing evaporative cooling. Sweat pours, heart rate spikes, and muscles demand oxygen faster than the lungs can supply it. Within seconds, breathing becomes shallow and frantic, driven by desperation rather than efficiency. Each inhale feels insufficient. Each exhale feels wasted. This is where lungs become the limiting factor. Not strength, not courage, physiology. As breathing degrades, coordination follows. Your stride shortens. Foot placement becomes sloppy. Routes that were manageable at walking speed become trip hazards at a sprint. Vines snag ankles. Saplings flex underfoot. The understory does not forgive haste. Panic running turns the ground into a trap field. A stumble is often all it takes. You catch a root, pitch forward, and hit the ground hard. The impact drives air from your lungs again, compounding the first breath loss. Dust, leaf litter, and debris flood your mouth and nose as you gasp reflexively. For a moment, breathing is not just difficult, it is disorganized. Inhale arrives too early. Exhale cuts off. The body flails for rhythm and fails. From the herd's perspective, nothing extraordinary is happening. Peccaries are responding to perceived threat by asserting space. White-lipped peccaries in particular are known for large herds that can number in the hundreds, their collective movement reshaping sections of forest as they pass. Even smaller species like collared peccaries rely on group cohesion to deter predators. Jaguars, their primary natural enemy, understand this dynamic well. A lone peccary is vulnerable. A herd is hazardous. This is why the herd does not need to catch you. It needs only to outlast your lungs. Ecologically, peccaries are ecosystem engineers. Their foraging disturbs soil, redistributes seeds, and creates micro-habitats for insects and plants. Their trails become corridors used by other animals. Their wallows alter water flow. They are not fast runners in the marathon sense, but they are relentless movers. In dense forest, persistence beats speed. Humans misjudge this because we associate danger with pursuit. We imagine being chased down, tackled, overpowered. Peccary encounters are different. The danger lies in displacement and exhaustion. If you fall within the herd's movement path, trampling becomes a real risk. Hooves do not aim. They strike where bodies land. A person on the ground is suddenly at the wrong height in a system built for low forward momentum. Breath control collapses completely in this scenario. Between impacts, exertion, and panic, the respiratory system cannot stabilize. Hyperventilation alternates with breath holding. Carbon dioxide levels swing wildly, worsening dizziness and confusion. The body wants to get up and run, but coordination is gone. Muscles fire out of sequence. Balance feels unreliable. This is when injuries escalate from manageable to severe. Peccaries do not need tusks to be lethal, though they have them. They do not need to single you out. They do not need to chase beyond a few dozen meters. The environment amplifies their effectiveness. Dense vegetation channels movement. Heat drains stamina. Uneven ground punishes haste. The herd's role is simply to apply pressure until something gives. From a biological standpoint, this is an elegant strategy. It minimizes risk to individuals while maximizing deterrence. Predators that test a herd learn quickly that persistence favors the group. Even apex hunters like jaguars pick targets carefully, isolating the weak rather than confronting the mass. Humans, lacking that discrimination in panic, often do the opposite, charging blindly into worse conditions. There is a subtle sensory component to this encounter that deepens its impact. The sound of a herd moving through brush is overwhelming, filling auditory space and drowning out other cues. Vision is fragmented by vegetation. Smell carries musky animal intensity that triggers primal alarm. The brain processes all of this as imminent threat, accelerating stress responses that further degrade breathing and judgment. The irony is that stopping, orienting, and controlling breath often reduces risk. But those actions feel impossible when every instinct screams to flee. This is the rainforest's most consistent lesson. Survival depends less on raw output and more on regulation. Peccaries exploit the opposite. As the seconds stretch, lungs burn. Legs feel heavy. Sweat stings the eyes. The body feels betrayed by its own limitations. This is where the encounter resolves one way or another. Either distance is created and the herd veers off, satisfied that space has been reclaimed, or exhaustion forces collapse in a place where recovery is slow and dangerous. The herd does not celebrate. It does not pursue vengeance. It moves on, resuming foraging, its internal cohesion intact. The forest absorbs the disturbance and closes behind it. What remains is the aftermath: shaking hands, ragged breathing, the realization that the threat was never speed or strength, but endurance. This chapter reveals a fundamental truth about large animal encounters in dense ecosystems. The most dangerous moment is not impact. It is the loss of respiratory control that precedes and follows it. Once breathing becomes inefficient, everything else degrades. Decision-making narrows. Coordination falters. The environment takes over. Peccaries do not hunt humans. They do not need to. Their defense is built around forcing mistakes under pressure. They turn your own physiology into the bottleneck. In humid heat, with obstacles underfoot and panic in the bloodstream, lungs become the limiting factor faster than any predator ever could. Your lungs are your limit. The herd doesn't need to catch you, it needs you to burn out. The jaguar does not announce itself because it does not need to. In the Amazon, silence is not absence, it is dominance. Along a trail edge or riverbank, where vegetation thins just enough to suggest visibility, the forest feels readable. You can see farther. You can hear water moving. You tell yourself that if something large were nearby, you would know. That assumption is the jaguar's greatest advantage. By the time you are aware of its presence, the most important decision window has already narrowed. Unlike herd animals or territorial defenders, the jaguar does not rely on pressure or chaos. It relies on timing. Its movements are deliberate, measured, and often invisible until the final seconds. Jaguars hunt by controlling space before they control bodies. They choose angles that limit escape routes, use vegetation to erase their outline, and approach close enough that speed becomes irrelevant. There is no chase in the cinematic sense. There is only positioning. The moment of awareness is often subtle. A shape that does not resolve cleanly. A shadow that holds its place when others shift. A sound that is too controlled to be accidental. Your brain registers it before your conscious mind does, and the response is immediate and profound. Muscles tense. Blood pressure spikes. Breathing accelerates. This is the breath hijack moment, and it arrives before any physical contact. Freezing is not a failure of courage. It is a neurological reflex. When confronted with a high-risk predator at close range, the brain suppresses movement to avoid triggering pursuit. This can be adaptive, but it comes at a cost. While your body locks down, your respiratory system surges. Breaths become shallow and rapid, drawn high in the chest. Each inhale sounds louder to your own ears. Each exhale feels incomplete. Coordination between breath and movement breaks before movement even begins. Jaguars are exquisitely tuned to this state. Their sensory adaptations favor detection of disruption rather than noise alone. Low-frequency sounds, irregular movement, and changes in posture all register quickly. While they do not track breathing in the literal sense, the physiological consequences of panic, stiffness, imbalance, erratic motion make prey easier to predict. A controlled animal is difficult to read. A panicked one is not. If the jaguar commits, it does so with decisive control. This species is unique among big cats for its killing technique. Rather than targeting the throat to suffocate prey, jaguars often deliver a crushing bite to the skull or cervical spine, using immense jaw strength to disrupt the nervous system directly. This is not about prolonged struggle. It is about immediate shutdown. Control the head, and breath disappears fast, not because air is blocked, but because the systems that regulate breathing are incapacitated. But escalation does not require a full attack. Even without contact, panic breathing changes how you move through the environment. Fine motor control degrades. Balance becomes unreliable. The rainforest does not forgive that loss. Roots, slick mud, uneven banks, all become hazards when posture and breathing are no longer synchronized. A slip on a riverbank or a fall on a trail edge creates noise, injury, and vulnerability in one motion. The forest does not need the jaguar to finish the job at that point. Everything else is already in place. From an ecological perspective, jaguars are not reckless hunters. They are energy economists. Failed pursuits cost calories and increase risk. This is why they prefer ambush over chase, proximity over speed. They select moments when prey is already compromised by terrain, by distraction, by physiological stress. Humans rarely consider themselves prey, but the jaguar does not evaluate identity. It evaluates opportunity. Jaguars occupy a unique niche as apex predators that bridge land and water. They hunt deer, peccaries, capybaras, caimans, even turtles adapting their tactics fluidly to environment. Along riverbanks, they use reflections and vegetation to mask approach. On trails, they exploit bottlenecks where movement options collapse. Their rosetted coats are not camouflage in the abstract. They are disruption patterns designed to fracture outlines in dappled light. Even when visible, they are difficult to resolve clearly enough for accurate reaction. The psychological impact of encountering a jaguar is inseparable from its physical threat. Humans evolved to fear large cats for good reason. The brain's alarm systems activate rapidly and intensely, often overwhelming rational thought. This is why breathing control becomes so critical. Once respiration is compromised, decision-making narrows. You lose the ability to assess distance, choose footing, or modulate movement quietly. Everything becomes urgent, and urgency is loud. Breath gives you away not as sound, but as motion. Rapid breathing shifts the shoulders, expands the chest, alters posture. In still environments, these micro-movements matter. Predators detect pattern changes far faster than humans do. A body that suddenly stiffens, leans, or sways stands out against static vegetation. The jaguar does not need to see you clearly to know where you are. There is a cruel irony here. Many survival instincts that serve well in other contexts, running, gasping, bracing, work against you in this one. Jaguars excel at exploiting transitional moments when prey shifts from one state to another. The instant you decide to flee, to turn, to step backward without looking, you expose yourself to terrain-induced failure. A fall does not just injure, it strips control completely. On the ground, breath is harder to manage, orientation collapses, and defensive movement becomes inefficient. Jaguars have been observed abandoning pursuits when prey maintains composure and awareness, choosing instead to conserve energy. This does not mean calm guarantees safety, but it highlights the role of physiological regulation in survival. Panic advertises vulnerability. Control obscures it. Ecologically, jaguars shape entire ecosystems through fear as much as predation. Their presence alters prey movement patterns, grazing pressure, and habitat use. Trails shift. Riverbanks empty at certain hours. This cascade of effects, known as trophic regulation, demonstrates how a single predator influences landscapes without constant killing. Humans entering these systems are subject to the same pressures, even if encounters are rare. The rarity of jaguar attacks on humans often leads to complacency. But rarity does not equal impossibility. Most incidents occur at edges, where forest meets water, where trails intersect hunting grounds, where visibility tricks the mind into underestimating concealment. The jaguar thrives in edges because edges compress options. They are places of decision, and jaguars specialize in shortening those decisions. The most dangerous moment is not when the jaguar appears. It is when your breathing changes. That shift marks the transition from observer to participant. From that instant on, your physiology is part of the encounter. Every breath affects posture. Every posture affects balance. Every imbalance affects outcome. This chapter is not about portraying the jaguar as a monster. It is about understanding it as a predator refined by millions of years of selective pressure. Its power lies not just in strength, but in precision, physical, temporal, and psychological. It hunts the instant when systems falter, when breath becomes noisy, when movement becomes sloppy. Even without teeth on skin, Panic breathing ruins stealth. It ruins footing. It ruins awareness. And in an environment layered with other hazards, cuts, infections, insects, water, those failures compound quickly. The Jaguar does not need to finish the process. It only needs to begin it. The final truth of this encounter is simple and unsettling. The Jaguar is not waiting for you to run. It is waiting for you to lose control of yourself. Your breath is the first thing to go, and once it does, everything else follows. The Jaguar doesn't just hunt bodies. It hunts the moment your breathing gives you away.